Okay, let's start. And before we start, I would like to announce that we will be offering some help sessions next week. And it's like normal, we will offer help sessions before the week of the deadline of the assignment submission. So you can come to us, you can join us in person if you are on campus. And if not, because next week is flex week, so you can also choose to join us from online through the Teams meeting link. If you have any problems with assignment tool or just anything, so please feel free to join. And let's start today's learn content. So yesterday we have learned different levels of testing, and we learned actually four different levels: unit level of testing, integration level of testing, and system level of testing, and also acceptance testing. And we will be covering like unit testing, integration testing, and system testing in detail, like we have discussed. And yesterday we have covered unit testing and integration testing. And now let's learn system testing. And we will also be learning some test automation and scaffolding techniques today. So, so before we jump into detail, let's have a quick recap of what we have learned so far, so we know where we are on the like overall roadmap. So we have learned in week two, we have learned functional. In week two and week three, we have learned functional and structural testing, right? And all these techniques we have learned are all about how do we design the test inputs or the test suites, right? So for functional testing, we are designing the test inputs according to the requirements or specifications. For structural testing, we are designing the test cases according to different coverage criteria, right? So, and in this week, we are learning different levels of testing. And different levels of testing doesn't affect how we design the test cases. Instead, it actually affects the testing target. So we are testing a unit, we are testing a subsystem, or we can test the entire system. So it's more about what is the target. And the unit testing is normally done by the developers during development. And for integration testing, the key is more about how do we build different integrations, right? Because we have so many units, we can combine them in many different ways. But how do we systematically extract the subsystem is the key for integration testing. And for system testing, actually, what we will be learning is more about how do we design functional system tests or non-functional system tests. And this non-functional here is not the same as like, if it is not functional, then it's structural, then it is not the same case. We will be learning about this later. So we have learned this so far. And system testing, like, again, there's a very formal definition in the textbook. So it is conducted on the complete integrated product. So it's like we try to test everything here. So this is the keyword. And it is, and remember we learned the big bang integration, right? Which is also to complete to combine everything together for testing. The difference is that for system testing, we care more about testing the system's behavior against the specific requirements. So it's more about testing against some high-level requirements. And we can test it for both functional and non-functional aspects of features. So out of the three different levels of testing we have learned, system level of testing is the closest to our everyday experience. Because normally as a user, we don't like use like just a unit of the function or just a subsystem of the function, right? We just use the entire function. the entire software. Sorry. So here the key here is how do we. So what is like functional versus non-functional? So for functional testing, the target we are testing is the business logic or the core features of the software. And normally what we do is we provide the input and we check the output against some like golden standard to check whether there is a bug or not, right? So for this, we just so this is the functional aspect. However, for the non-functional aspect, it is not the same as structural. So what we care is we instead of testing the main features or main business logic, we care about other aspects which can affect the performance of the system in real world, like for example, the scalability, the usability, and other like quality attributes. And normally for these attributes, we don't have like a golden standard like to tell us whether there's a bug or not, right? So we have to evaluate them on some other performance criteria. So this is the difference here. And let's take a look at an example to see what's the difference between these functional aspects and non-functional aspects. So I believe all of you have seen this before, right? This is a tran, and you can see the keyword test from this photo here. And actually, I think they are actually actively testing the system or upgrade or doing some maintenance of the system during weekends. Because during weekends, sometimes if you take the tram to the city, you cannot directly take the tram to reach to Circular Quay. You will stop at the service will just stop at Central Station, and you have to go to Circular Quay like by train or walk there. Just so because they are doing some maintenance and testing during weekends. And for this system, we can we can think about some functional aspects for testing this system. So for example, we can test the tram scheduling system. We can see if, because there's a timetable, although they may not strictly follow the timetable, but there is a timetable. And we can check if the tram services are running according to the published timetable, right? So this is considered as a functional test. And we can also test the passenger's information system. If you get into the cabin of the tram, you can see there are some small screens showing maybe the next station, right, and the planned arrival time kind of thing. So we can verify the correctness of this passenger information system. And this is also considered as a functional test. And for non-functional, it is more about all the other quality or performance-related issues other than the main features or main functionalities of the system. So what we can think about is, for example, we can test the scalability of the entire system. So what if we have a larger number of passengers, like, for example, if there are some games, sport games in the stadium, so there will be a lot of passengers, right, on those days. So if there are such events, can this system still handle the passengers properly or not, right? And we can also try to test the maintainability of the system because they are like regularly maintaining this trans service, and especially during weekends, and we can try to assess how easy it is to perform these maintenance tasks, right? So you can see that functional testing cares more about does the system do the right thing? And for non-functional testing, it is more about does the system do it well enough? So so the difference is where it's kind of clear, right? So functional is more about the tasks, the major tasks or the main functionalities of the system. And non-functional tests care more about other performance-related qualities. So this is the example. And let's have a warm-up lab poll. So for security, security is like a special property for many software systems, right? So is security considered as a functional feature or non-functional feature in software systems, according to what we have just learned from the definition and example? I'll give you some time to finish this. So, so there are some hints or tricks for doing multi-choice questions. If you see something like this, normally this is the correct answer, right? So in this case, the third option is the correct answer. And let's see the results. And actually, most of you chose non-functional, and this is kind of expected because for most software systems we are using nowadays, security is not a functional feature. But for some special software systems, like for example, the firewall, then it is security is a functional feature, right? Or maybe a malware scanner, a malware reporting like scanning software, then it is, or virus scanning software, then it is a functional feature. So it depends on the software system we are testing. So security could be either functional or non-functional. But for example, for web CMS, security, I think it should be a functional feature because otherwise students can hack into the system and then modify the marks, right? So this is a functional feature. So, but for some other systems, maybe like for Google Drive, for this Google Slide, then security is not really a functional concern, right? So it depends on the system we are trying to use, we are trying to test. So, so as you can see, because of the diversity or variety of software systems, so there could be a lot of non-functional features we can care about, right? So now we have learned about functional and non-functional aspects. Let's do a comparison between these two aspects. So first, so we don't have to go through all the things in detail, but we just highlight some key things here. So normally for functional testing, we are collecting the errors from the implementation. But for non-functional testing, we can collect errors from the architectural design. So maybe you have learned about different software architectures before, or maybe not, but it doesn't care. It doesn't matter here. So we just need to know that if given a specific requirement, a list of requirements, we can design the software system in many different ways, right? We can use different patterns. For example, we can use layer patterns, we can use server client pattern, we can use like other different architectural patterns. But these architectural patterns doesn't affect whether the code is following the specifications or requirements or not, right? However, so that's why for functional testing, normally we cannot capture the errors or the bad designs in the software architecture. However, if we do non-functional testing, we may expose some shortcomings or limitations of the architecture design. Because if we don't use a good software architecture, then the system may not be scalable enough, right? It may run very slow, so the performance could be bad. So that's why non-functional testing is good at exposing the design limitations. So this is like a comparison, and you can go through the rest of the points by yourself. So now let's think about different techniques for system testing. So the first set of technique is related to functional testing, system level testing. So it is called model-based testing. It is a big family of techniques. And you don't need to learn all the like very detailed technique here in this lecture, because the purpose of this lecture is just to go through all the different concepts so you have something in your mind, and when you see some keywords in the future when you are working or when you are doing something else, so you know that, okay, this is something I have learned, so this is the purpose. Because we have learned some model testing techniques in detail before this lecture, and I will tell you. So model-based testing is for testing is a family for functional testing. And as indicated by the name, we should utilize abstract models for guiding the testing process. And the reason for doing this abstraction using the model is that because we can model the system into some specific type of models, right? Then we are getting rid of some details. Because we are getting rid of the details, we can apply some very powerful analysis techniques. Because these powerful analysis techniques are often not very scalable. We have to drop some details. We have to focus on the key features we care about. So that's why we need some kind of abstraction with the models. And as you can see here, the key for model-based testing is all about the choice of different models, right? And what kind of models we can use, right? So we have many different models. And these models can be extracted either from the requirement or the actual implementation. So, and we have learned one requirement-based model before this class. Can you think about that? What is the model we have learned? For functional testing. So model-based testing is for functional testing. So what have we learned for functional testing? Boundary value, equivalence class, and what else? Decision tables, right? So actually, decision table is a type of model we have learned. It is for model-based testing. So and of course cause effect graph, which can be which is helpful for deriving the decision table. So this is actually a model. Decision table is a model. So that's why we don't need to learn in detail about all the other techniques here, but we just quickly go through them and to help you to have something in your mind. So here are some more typical models. So first is finite state machine. So a finite state machine actually looks like this. So it is like it is made up of it is like a graph, and inside this graph, each node is like a state of the system, and each edge is an action that we can take to make the state transitions. And finite state machines are normally useful for modeling the systems that clearly have different states. For example, if we implement user session maintenance system. So we clearly have the different states, right? Like whether the user is logged in, logged out, whether the user is holding a session or not, right? So this is one example. Another example is like the vending machine. So the vending machines can have different states, right? They have the idle state waiting for you to put in some coins, and they have the state of waiting for more coins, and they have the state of giving you the product, right? So this is finance state machine. And another graph related model is called Hatchet-Knight. And this is a very old technique. So finite state machine is still very useful nowadays. But Hatchet-Knight is a little bit old. It is used to describe the concurrency of different systems. You can think of it as an enriched version of the state machine. So inside the Packard we have different places. So these circles here are just places indicated by P1, P2, P3, P4. And each rectangle here is like an action we can take or a task we are going to do. And each black dot here is like a token we are holding. So these tokens could be system resources. So for example, this token could be like we are holding like one hard disk instance, and this means we are like holding two resources here, right? So we can clearly see how different states are, how different places are using different um, resources of the system. So this can help us to describe to better deal with concurrency and the synchronization. So this is the Hatchet-Knight. And another type of model is called context-free grammars. So it is used to model the system's input-output language using some rules. And this is like the definition of this context-free grammar. So you don't need to learn this in detail, but you just need to have something in mind. Okay, there is a model called context-free grammar, and this context-free grammar could be used to describe highly structural system inputs or outputs. And one example of structural system input and output is programming language. So normally, almost all the daily used programming language you are using right now, for example, Python or Java, they could be described in context-free grammars. So, and you can imagine if we want to test the interpreters or compilers of a programming language, then we can use context-free grammars to guide the generation of these input, right? So this is context-free grammar. And of course, we have our old friend, the decision table. So actually, this is from a lyric of the song. So hello, decision table, my old friend. So decision table is actually used to capture the behaviors of the system, and it is used to reflect the correspondence or relationships among the actions and results, right? So among the conditions and actions, right? So we know that decision table is like one of the most detailed approach for like capturing the system's business logic, right? Comparing to boundary value testing and equivalence class testing, it is more fine-grained decision table. However, decision table still have some pitfalls comparing to like other models, because normally we are grouping the decision table results according to the actions, right? We are trying to capture all the different actions. However, the system could have very complex with the systems could have very complex inputs, but take very simple actions. And in that case, decision tables are not good enough to capture the diversity of the input space. So let me show you an example. So imagine we have a very big Q&A system that can answer like any yes or no questions. For example, so this is a system we have. Sorry, the ordering of the attention is bad again. So let's say if we ask, is computer photo a good course? And the system will just answer yes. So, and if we ask, is Sydney in the Victoria state? Then it will answer no. So basically, this system might have like two different systems inside, right? So the first question is more about reasoning because we don't know whether this course is a good course or not. We have to go through some reasoning process to reach out the result, yes. And for the question of is Sydney in Victoria, then it doesn't have to do any reasoning, right? It just need to do a fact checking, right? This is similar to how these big chatbots, like powered by large language models, are built nowadays. So it doesn't have to do any reasoning. You just need to do a fact checking. However, if we just use the decision table to model this system, you can imagine that there are only two actions. No matter how like diverse the questions could be, there are only like two outputs, two actions from the system. So we may only eventually build two test cases from if we use decision table, right? And in this case, this is like we are falling into the pitfall of oversimplification because we don't is omitting the diversity of the input space. So this is the pitfall of decision table. And there are some other models as well. So another model is called Markov chain. So it is like, again, it is a graph-based model. So it is used for capturing the probabilistic of jumping across different states. So this is, as you can imagine, this is a person's name, and this person is from Russia. And this Markov chain is actually it is useful when the system to capture the probabilistic of jumping from one state to another. And actually, almost all programs we are using nowadays can be modeled by Markov chain. The reason is that let's imagine this program here. So we can trigger a crash if the string is bad, right? And let's assume that we are generating a random input as the string. Then the chance of passing the first if is like this, right? Because we have because if we just randomly generate the string, there is a chance that we can make the first character correct, right? And only if we make the first character correct, we can get into the second state, right? And only if we are getting to the fifth state, we can get the correct answer, right? So we can actually calculate if we assume that the input is purely generated randomly, we can calculate the chance of reaching any location in the program, right? Because we can collect the conditions here and we can calculate the chance of making the condition to pass, right? So in this case, we can model the chance of jumping from one state to another. And this model is called Markov chain. And this Markov chain is helpful for testing because once we can get all the different probabilistics, we know that some part of the programs are easier to reach than the other places in the program. And the places which are harder to reach are the places where the bugs are more likely to happen, right? Because if a place is like very easy to reach, then it could be used could be verified by the normal inputs used by the users. So it's much easier to spot the bugs. But if it is located in some places where the reaching probability is very low, then it could be hard to find those bugs. So that's why because this gives us this can tell us whether a place in the program is easy to reach or hard to reach. It is very helpful for random testing or fuzzing. We will learn about fuzzing later. So if we just generate test cases randomly, then this could be helpful. So I won't go through the detail of why this is calculated like this. You can calculate yourself if you are interested. And now let's learn different non-functional testing. So we just know that, okay, so functional testing, we can have many different models. And for non-functional testing, it's all about the other factors that may affect the performance of the system, right? So it involves actually comparing to functional testing. It involves more time, effort, and resources. We will know that. So the key here for preparing the non-functional testing is that we don't care about the correctness of the functionalities of the features. We care more about the performance. So what we need to do is we need to create a near real life environment for us to run the software. And then we can collect the details like about how the hardware setup, develop the deployment information, etc. In advance. So does this remind you of something like setting up a configuration to simulate the real usage scenario? Does this remind you of some keywords, some techniques we have learned before? Can you think about it? So when we talk about setting up some like usage profile kind of thing, like what is related to usage profile? We have learned when to stop testing, right? And during the learning of when to stop testing, we learned statistical testing. And for statistical testing, we are testing the reliability of the software, right? And in order to test the reliability of the software, we have to simulate how the real users are using the software. And in order to simulate how the real customers or users use our software, we have to collect usage profile. We have to set up a simulation environment. And this is actually very similar to that one. So normally we care, this is from the textbook, which is a little bit outdated. So normally we care about these four types of resources when we set up the environment. So we care about the network, we care about the disk, we care about the CPU, and we also care about the memory of the computer. And do you guys know the difference between disk and memory, right? So actually a lot of non-computer science people, they don't know the difference of disk and memory because they think everything is just memory. But actually disk is used for storing the data and memory is used as a temporary storage, which is used for by the CPUs, right? And nowadays, in the age of large language models, actually we care something else. So what else kind of resource do you think we should care about? We should also care about GPUs, right? We should also care about GPUs nowadays. And and sometimes, so there are some if you do AI or if you play games, you know that for GPUs they have like GPU memory or graphic memory. And now there's a new architecture used by some hardware, like for example this MacBook here, or a new hardware called DGX Spark, which is designed by NVIDIA. So they have some new computer architecture that allows CPU and GPU to share a big pool of memory. And because they are sharing this big pool of memory, we can load some like large language models into the memory and do inference. So that's a new type of computer architecture we are having nowadays. But this piece of knowledge from the textbook is very kind of old, so they don't talk about GPU there. But actually, in reality, nowadays we should also care about GPU sometimes. So non-functional testing is all about testing the other aspects that may affect the performance of the software. So it is also known as performance testing. And for performance testing, there are many different types. So we have load testing, which is to just check how the system behaves under normal or expected load. So it is called load testing. So for example, we can test the web CMS by simulating 500 students concurrently performing some random actions on this website, right? So 500 is actually an expected load because for some courses, there are like much more than 500 students. Right? So it should be able to handle this. So this is load testing. And for stress testing is to evaluate the system's behavior under some extreme conditions. So we need to we need to give the system a higher load than expectation. So this is stress testing. And an example is, for example, when we talk about stress testing, we need to specify the maximum number that the system can handle. So, for example, if a website is designed to hold 1,000 users, what we do for stress testing is that we can increase the user count to maybe 10,000. So this is stress testing. And there are some other types of performance testing as well. So we also have spec testing. Spec testing is like we test the system performance uh, by suddenly increasing or decreasing the number of users or the amount of load. So it's not about it's not just about the number here. It's more about the sudden increase. So it's like increasing the system's load in a short period. So what an example is, for example, we can. So sometimes students just like submit the assignments in the last maybe 10 minutes before the deadline. Then the system is under heavy load during that time, right? And you may encounter some system errors for give sometimes. And that is because you are kind of like automatically doing some spec testing for the system like that. And comparing to spec testing, we also have this endurance testing. So this is actually to ensure the system's speed, to test the system like beyond its expected working time. So and an example is like this. So for example, we are like actually there are some videos streaming services in this room right now. So which is known as Echo 360, right? So and it is working right now. And what if we just it is automatically turned off after 2 hours, and we know that it may work properly during these 2 hours. But sometimes, like during the start of a term, these systems may break in the classroom or something like that. But we know that now it works for 2 hours. But what if we let it run over time? Like, what if we don't turn off this streaming service for after the 2 hours? What if we let it run for 48 hours? What will happen? So this is like endurance testing. And actually this, uh, I believe some of the Chrome, the Chrome on Mac may need to do better endurance testing because as you can see, the tab is consuming a lot of memory of the computer. You can see if I don't turn it off, it may increase over time as well. You can see it's consuming like 142 megabytes of memory with this simple tab here. And this simple web page should be just a few hundred kilobytes, but it's consuming like 140 something megabytes of memory. And for some cases, if I open like a YouTube page, a YouTube video, and don't close that tab, there could be some memory leak, and I think the the memory usage could be a few gigabytes in that case. So this is endurance testing. And we also have a set of scalability. We also have scalability testing for performance testing. So scalability testing is to test the system's ability to scale up and down on demand. So by adding like or removing resources. So scalability is more about whether we can have enough resources to deal with the situations or not by like adjusting the resources we provide. So an example is we can gradually increase the number of the servers and database instances to see if it can handle the increasing number of users. And a typical example of this is for cloud services. If you are familiar with AWS, you know that if you are familiar with like almost all the cloud service providers, they provide this. So they can charge you as a constant rate by allocating you some fixed resources, like maybe 2 gigabytes of memory, one CPU, and maybe the bandwidth of the network is also fixed. So they can charge you in that way. And they also allow elastic instance, which means that, let's say your system is designed to handle 10 users at the start. So they will allocate you maybe one virtual machine, one instance of the virtual machine to host the server. So you can handle the 10 users responsibly. But what if your system, like you have built very successful product and you have maybe 1,000 customers, then this one single virtual machine may not work, right? Then the cloud service can automatically allocate more like virtual machines to host your server. And this automatic allocation of resources is known as elastic instance. So, and this is related to the scalability of the system. So it's just to test whether the system can scale up and down. So this is scalability testing. And then we also have yet another performance testing, which is called usability testing. So it is actually related to assessing whether the user can use the system easily or not. So, for example, we can give a healthcare application to a group of doctors or patients to see if they can like use the app normally, like easily or not, right? And this is actually related to HCI, and we do have some HCI courses here, and we won't go through that in detail. So it's more about like human-computer interaction. It's more about the UI and UX testing. And we also have yet another testing, performance testing, which is known as compatibility testing. So compatibility testing is to ensure that the different components of the software are compatible with each other. So this, for example, we can test the mobile app with like Android or iOS, and we can also test these apps with like different uh, devices with different sizes of the screen, right? And this is normally the compatibility testing for is normally used for like mobile apps and web pages. And for example, maybe you know this before, but maybe not. So, for example, all the all the web pages nowadays should be responsive. And responsive means that the web page can work properly under different program sizes. So for example, if you click on the inspect or you can get to the developer tools, you can click on this button here. So this can help you to simulate different sizes of the screens. So for example, this is how this web page, how this live poll will look like on an iPhone 14 Pro phone. So it still looks quite good, right? So this means that this web page is designed to be quite responsive. And of course, you can also try out different program sizes. For example, you can try out an iPad. So this is how the web page will look like on an iPad. So this, so you can see that we have to test we have to do some compatibility test because the software we have developed may run on different devices or different environments, right? So that's why we need to do compatibility testing. And our old brand availability testing is is one of the non-functional testing. So you have learned it before. So it is related to like uptime or downtime, right? And we have seen the cloud status page, which is related to availability of the cloud service. And we know that, okay, if it is like, it's all about calculating the uptime and downtime of the system. So this is availability. And also we have availability belongs to part of the reliability testing, right? So the reliability testing is to run the system during a period of time and observe whether there are anything wrong or not. And for reliability testing, we have different metrics, right? We can count the errors according to the number of requests. We can count the number of errors during a fixed period of time. So there are different metrics here, there, and we have learned it in the when to stop testing lecture. And this is just a quick recall. And you know that reliability reliability testing is actually kind of overlapping with several non-functional testing techniques as well. For example, availability testing, right? It's, it's a big family here. So let's, before we end the first half, let's let's do a live poll to practice whether you have learned about the different non-functional testing techniques good enough. So we have learned so many non-functional testing techniques. So which non-functional testing techniques are these two example requirements related to? Like the first one is if we query 1,000 records, it should have a response time less than 3 seconds. And the second one is, let's assume that the system can only take 20 clients. Then we test the system with 25 clients. So for load testing is to test the system's behavior under normal usage load. For scalability testing is to test whether the system can allocate more resources for more user to handle more user requests, right? And for stress testing is to test whether the system can behave properly beyond the maximum expected number of users. So do you think we have scalability testing here? No, right? Because we are not dealing with any resources here, so we can quickly rule out option 1 and option 4. And then we need to think about which one is the stress testing. Because we specify the maximum number of clients in the second requirement here. So the second one should be stress testing. And since we didn't specify like what is a normal load, like what is the maximum load, so we just assume that 1,000 record is just normal. And then we are doing a load testing for the first case. So this is the correct answer, and let's see the results. Okay, it seems most of you can get it correct. And that's all about the first half of today's lecture. And let's have a 10 minutes break. I will see you at 4:07. Okay, let's continue. So just now we have learned different system testing techniques, basically two big families, functional and non-functional. And now let's learn about test automation and scaffolding. So we have covered so many techniques to derive test cases for different test terms, right? So, but how do we but we don't cover how do we actually use these test cases after generating them? So normally, how do we run these test cases? Like when you do assignment one, or if you have started assignment two, how do you run the test cases? You just normally run the code and check the results by hand, right? But please don't do this in practice because in practice we have a lot of test cases. We have very large projects, and it's impossible to just manually run everything. And if you take a look at on GitHub, you can see for many projects they have CI and CD pipelines, right? They have many, for example, they have many mm, they have many actions after you make a commit to the code. So these actions can automatically build or test the system. So we should do this. If after creating the test cases, you should create some automated approach to run them just because humans are very slow and very expensive and sometimes error prone. And test design requires actually effort and creativity, as you can imagine, because we need to think about how to approach the problem from a different angle, like how to cover the different corner cases. So test design should be creative and should require you some effort. Then executing the tests shouldn't cost you a lot of effort. So we need to think about how can we automate the process of executing the tests we have created. And just now, the CI CD pipeline on GitHub is an example. So by definition, test automation is like the development of software to separate the repetitive tasks from the creative aspect of testing. So we can somehow write some programs to automate this part of the tasks. And automation allows us to control how the test how and when the test cases are executed. For example, we can control the conditions and preconditions and the environment for running the tests. And we should automatically compare the results, right? To report bugs, we should be able to automatically report bugs. And we should automatically be able to run the test cases. For example, when we submit a git commit, we should be able to automatically trigger some tests, right? So this is automation. And to do this automation, we need test scaffolding. So which is to write some small programs to wrap around our test cases so that we can run them automatically. And normally the test scaffolding code is not, you can imagine it's not considered part of the product. And most of the time they are temporary. Just like the scaffolds we use for building the buildings, for the constructions, right? We are removing them once the building is built. So it's similar for test scaffolding. And this is a typical or a complete structure for test scaffolding. You may not need all of them in the test you are writing, but this is just everything here. So let's go through the components one by one. So this program unit is the target we are trying to test. It can be a unit, it can be a subsystem, or it can even be the entire system we are trying to test. And a harness, we have encountered the concept of harness before today's lecture. In yesterday's lecture, we have encountered the concept of harness. So harness is used for the top-down integration, bottom-up integration. So it is used to substitute the wrapping the environment for running the program unit. So harness, so the gray part of this in this graph, the program unit is the actual concrete code we would like to test. And harness is just to prepare the environment to run this gray part of the code. And if like let's say the unit is just a single function, and you haven't implemented other functions yet. So what you can do is you can, and this function depends on some other functions. So the dependent function, for the dependent function, you can just write it into the harness, like writing some mockup features in the harness so that this program unit can run properly. So this is the harness. So the harness is like wrapping up everything here. And the driver is like the color of this target we are trying to test. So sometimes, let's say we don't have the color implemented, then we can just use a driver. And sometimes talking about color, we do have calls, right? Sometimes we don't have the calls of the target function implemented. Then we just replace them with a stub. So driver and stubs are just like mockups of colors and calls. And of course, the purpose of tests is to capture bugs, and we need to have some ground truths to compare against to find bugs, and we need to do output comparison. And this is also known as test oracle, and we will learn about how do we derive test oracle automatically later. But now we just need to know that, okay, we need to do some after running the program unit, there are some outputs, and we need to compare it with some ground truths to look for bugs. So this is needed. And sometimes we also need a tear down because some tests, because we are actually executing the program. And executing a piece of program sometimes may require us to acquire some system resources. For example, if we are testing a server, then this server is occupying some parts of the program, of the device, right? And if we are running a client, then this client may hold some connections to the database, right? Then the connections to the database are the resources we have that has been allocated for running this program. We have to gracefully release the resources we have occupied during testing. So this is called tear down. So this is also needed sometimes. And this is also to it is important because let's assume that you are testing a server, and each time you are allocating like maybe the port 8080, then if we don't do tear down, the next test will fail, right? Because we cannot allocate the same part to different processes, right? So we have to prepare a clean state for the next test. So that's why we need to do tear down. And there are several, so that's the structure of the test scaffolding. And in order to actually implement this scaffolding code, there are some frameworks that you can use for different programming languages. And for Python, you can use PyTest, those two. For Java, you can use JUnit. For JavaScript, you can use Jest or Mockito. I think you have been using Jest for 1531, and for C or C++, you can use gtest. So these are the frameworks that you can use, and they often call themselves unit test frameworks, but actually they are not strictly unit tests, because the program unit you are writing sometimes are like integration or subsystems. So it's actually a mixture of unit test and integration test. Normally, the normal so-called unit tests we are writing every day. So for Rust, you have the built-in testing framework. And here are some examples of different testing frameworks. So you can see this is an example of PyTest. So can we identify some like key structures, like correspondence between the structure and the actual code? So for example, so this is another example. So let's say we would like to test this. We would like to test this add here. Then this entirety of this entirety test calculator with stub is considered as the harness. And this adder stub is the stub, right? It is to replace, because we are testing the calculator app, and we haven't assumed that we haven't implemented the adder stub, the adder the add function of the calculator yet. Then we can replace it with an adder stub. So this is what we can do. And of course, you can see this part is the output comparison in the test scaffolding structure. And now let's see another example of JUnit. So JUnit is for Java. And for Java is a very typical object-oriented programming language. And in these languages, normally the definition of unit is different from like other languages. Like the entire class is considered as a unit. So for JUnit, let's try to identify the different items structures here. So for example, you see this at here is like an annotator of the function. So it means that before each test, this function is invoked. This function is invoked. So you can see add test means this function is a test, and before each is something that is invoked. So this before each, and you can see the after each is like what happens after. So this after each is clearly tear down, and this before each is actually the harness. And these are the actual units for testing, right? And this calculator.add is the program unit we are testing. And the 1, 2, and -1, 1, and 1, they are the actual test cases. And this assert equals are the output comparisons, right? So this is the correspondence for JUnit. And let's see another example for gtest. So this gtest is actually kind of similar to JUnit, right? We also have this kind of setup and tear down functions, and each one of the functions here is written with a macro, and each one of the macro here actually is like invoking the add function with a concrete test case, and is doing the output comparison here, right? So the setup is the harness. The tear down is just tear down, and each one of the expect equal is the output comparison. And you don't have to like you don't have to memorize all the like detailed all the detailed grammars for writing each one of the for using each framework here. What you need to know is just that about this structure here. So you know that you know what is a harness, what is a driver, what is a stop. I know that we should have output comparison, we should have teardown. And if you know this structure, you don't have to memorize like all the different grammars because like all of them are kind of the same as you can see here. So for G-test, they have this setup teardown. For JUnit, they have setup teardown. For PyTest, it's also very similar. So you don't have to memorize all the grammar, you just need to know the structure. And that's all for today's main content. And before we end today's lecture, let's have a review of what we just learned. So the purpose of learning this is not to learn. There are actually several tricks and tips for using these frameworks. For example, for PyTest, there are some tips for you to like write stubs or write drivers. But that's not the purpose of this course. The purpose of this course is to learn some transferable knowledge that you can apply when you do testing. It's not about like we learn any like a particular usage or some tricks for using some actual like concrete frameworks. That's not the purpose for this course. So you just need to know that, okay, all the frameworks are kind of implementing this kind of thing. So let's have a quick review of what we just learned. And as I'm talking here, you can try to remember or recall the concept, the keywords. So today in this week actually we are learning different levels of testing. And yesterday we have learned unit level of testing, we have learned integration level of testing. And now today we are learning the system level of system testing, right? And system testing is about testing the entire system against some specified requirements to see the to see the overall behavior of the system. And remember, system testing in the V model, where it is, right? It's one of the last step of testing before we release the product to the customers or the end users. And for system testing, it's all about testing the functional and non-functional aspects of the program, right? And for functional testing, we care more about does the system do the right thing? And for non-functional testing, we care more about how well does the system do it, right? And therefore, for functional testing, we have learned several techniques before, like boundary value, like Kuhn's class or decision table in detail. And now we learn a big family of functional testing, which is known as model-based testing. And for model-based testing, the purpose is to use some models to describe the system's behaviors so that we can apply different analysis techniques that could be applied to that model so we can derive test cases. And model-based testing is also to simplify the behavior of the system so that we can apply more powerful analysis. If we don't simplify this, then these powerful analysis techniques may not be scalable enough to be applied to these actual programs, right? And then for non-functional testing, it's all about the different other factors that can affect the performance of the system. Like, for example, we can do load testing. And what is the keyword for load testing? is just to test the system under the normal cases. And for stress testing is to test beyond the maximum allowed users, right? And what is like scalability testing? The keyword is related to resource, like whether the system can gradually allocate more resources to allow more users, handle more users. And of course, we have learned availability and reliability testing in the previous lecture when we learn about when to stop testing. And it's kind of also related to statistical testing, right? And there's one special type of, then there are two other types of non-functional testing, which is compatibility testing, which is to test, like it's often seen in the design or testing of web pages because different devices can build the web pages differently. So that's why we need to do compatibility testing. And the other type is usability testing, and it is more related to the UI and the UX, and it's related to human-computer interaction. And that's all about non-functional testing. And then we move on to learn test automation. The reason is that we would like to focus on designing the actual test cases, and that requires some manual effort, that requires some creativity. But once we have designed the test cases manually, we don't want to run them manually again, right? We want to have some wrapper programs that can help us to run the test cases and look for bugs. And this requires test scaffolding. And we learned about the typical structure of the test scaffold, right? On top, we have the harness that is to keep everything inside. And then for the color of the program unit we are trying to test, it is known as the driver. And for the callee of the program unit we are trying to test, it is known as the stub. And also, after executing the program unit we are testing, we need to do some output comparison, right? And after doing the output comparison, before we exit this single test, we also need to think about whether should we gracefully tear down this test or not. So this is typical structure of the program scaffold. And we also learned that, okay, for different programming languages, there are different frameworks that implement this test scaffolding structure. And we will be practicing using PyTest later. And that's it for today's lecture, and thank you for coming. Have a nice weekend.